This is a standard drill and tap index. You look down this side, the index, there are tap sizes listed for national course threads, all the way from 256 up to 1/2 13. On the other side, the index, are equivalent thread series in national fine, going from 264 up to 1/2 20. The row of drills here are the pilot drills for these tap sizes. The row of drills on the other side are the pilot drills for these tap sizes, and the drills in the middle are called body drills. For example, for a 1/2 13, the body drill is a 1/2 inch. So this gives you nominally some clearance between a 1/2 inch bolt and the hole that you've drilled with this drill. Going to be drilling a 1/4 inch hole through this piece of 1/4 inch stock. When drilling holes with an aspect ratio like this of about 1:1, it's often reasonable to drill the hole dry, that is, using no cutting fluid. Drill partway through, back the drill off to clear the chips. Down a little further, and drill through the part. That generally produces an acceptable hole. In fact, if you look closely, you can see nice clean finish on that hole. If you're drilling a hole with a much larger aspect ratio, for example, drilling a hole through this piece of 3/4 inch bar stock, the chips have more difficulty being cleared by the drill and being pulled up these flutes and tend to bind around the drill. So then it's a good idea to use some cutting fluid. Start as before with a center drill. And now move on to the 1/4 inch drill. This coolant and lubricant keeps the chips cool so they don't heat up and get soft, and it also lubricates the chips so they slide freely up the flutes and are cleared out of the hole. Now, often when you're working with large pieces of material like this, you'll be using large screws, bolts to fasten them together to other parts. In that case, what you often want to do is step up in drill size. So rather, say, than starting out by drilling a 1 inch hole, you would start by drilling a 1/4 inch hole and then stepping up in size. This results in a much more accurate hole, and it puts less of a strain on the tools. The next drill I'll use on my way to drilling a 1 inch hole will be a 1/2 inch drill. You could hear that noise. It's called chattering. And that's caused by the drill deflecting and jumping around the hole as it's coming in contact with the part. This is usually an indication that I'm running the drill a little bit too fast. So we'll try that again, this time run it on a lower speed. The drill is cutting much more smoothly now. We continue as before, drilling for a while and backing the drill out and clearing the chips. Until we break through the other side of the part. We'll now step up to a 3/4 inch drill. Okay, the chattering is now bad even in the low range that I have the machine set in. So what I need to do now is change the transmission ratio so that I can run the drill at a lower speed. And that's done with the levers on the side of the machine. On most machines there'll be a little map like this that will tell you what the different settings of the levers will do in terms of speeds or feeds. Here, if I look, the levers are set. They're both off to the right. So I have them set in this position now, which is 410 RPM at low range and 820 at high range. Even 410 is too fast for this size of drill. So what I'll do is set the transmission down to, we'll set it down to 85 and 170, which means the lower lever can stay in the right-hand position, and the upper lever is moved over to the left side. This doesn't always work easily. Sometimes it'll go part way, like it is now, and stop. And the reason for this is that the gears in here are bumping into each other like this. The gear teeth aren't quite meshing. So as you change the transmission gears, you're sliding gears in and out of mesh. So what you need to do is rotate something, either the motor or the spindle, in order to get the gear teeth to align. The easy way to do this typically is to grab the spindle and turn it by hand as you're trying to engage the lever. Okay, it's now gone all the way over into the left position, and the transmission is engaged. Now when we turn the machine on, you can see a very big difference in the speed of the drill. And this has eliminated the chatter. The last drill we'll use here is a 1-inch drill. Now, all the drills I've been using that are larger than a 1/2 inch are called step shank drills. Fairly obvious reason for that. The drill body is typically larger than the shank of the drill. All these shanks are nominally 1/2 inch, and there is some step associated with going to the 1/2 inch shank to the larger drill size. If you look closely, you'll also see some flats on this shank. It's very important to align those flats with the jaws of the drill chuck. You can see that several people haven't done that, and the chuck jaws have clamped down on the round, smooth part of the drill shank. What happens there typically, and it's happened with this drill, is you take a cut that's a little bit too big, producing a little too much torque on the drill, and the drill spins in the chuck. It only spins for a while though. It spins until the jaws of the chuck get over the flats, and then locks the chuck down so tightly that you sometimes just have to throw the chuck away. You damage the chuck in doing that. So be very careful to make sure that the jaws are resting on these flats. With a drill this large, it's difficult to feed the drill accurately by hand. It's very easy to push a little bit too hard and have the drill bite into the material too much and damage the drill. Sometimes you can actually just twist the shank of the drill right off. So the drill this large, drilling harder materials such as aluminum or steel, it's a good idea to engage the power feed and have the machine feed the drill through the part for you. That's done on this machine with this knob here. See, it's marked in and out. We'll start the drill up and away from the part, turn the machine on, and turn this knob to in. If you look at what the handle's doing here, you can see that the machine is now feeding the drill for me. And it's feeding it in a much more controlled manner than I could possibly hope to feed it. So one more thing we can do here before we start drilling the hole is take it out of gear, bring the drill down until it contacts the part, and we can set the depth by moving the slider up and down. Set it 0 here. This piece is 3/4 of an inch thick, so if we set this at about an inch up from this contact, the drill will proceed through the part, slightly beyond the part, until this comes in contact with this lever, and this lever then kicks the machine out of the power feed and retracts the drill. And that's all done automatically. While all this is going on, the machine's doing all this work for you, you shouldn't shut your brain off. You should continue to listen to what the machine is doing and watch what's happening. If you start hearing any strange noises, say the machine is starting to work harder and harder, stop the machine. Find out what's going wrong. You could hear the noise the machine there was making. Quieted down a little bit. That's the point where it broke through the other side of the part, proceeded a little further, and now pulled the drill back out of the part. The automatic feed and the feed stop are both very handy features if you're doing this sort of work all day long. You can see, if we look closely here, got quite a good surface finish. The other advantage of stepping up sizes of drills to the final drill size is that the hole that results is also rounder than the hole that you get if you just drill the hole with the nominal drill size right from the start. There are several other series of drills in addition to the standard series of fractional drills. It's a set of letter drills from A to Z, and these give you a little bit more resolution in the range from about 1/4 inch up to about 3/8 of an inch. The low end of the scale is a standard set of number drills. The standard set is numbered from 1 to 60, with 60 being the smallest drill and 1 being the largest. These are the 3 standard series of drills you'll find in most shops. For drilling very small holes, the series of number drills continues in another less standard series up to size 80. Those are drills. You'll have to take my word for it. They have flutes, just like the bigger ones. These are about 15/1000ths of an inch in diameter. With the bigger drills, you drill a few holes, have a look at the drill. If it needs sharpening, you sharpen it. With these drills, it's very difficult just to tell if there's a point on there at all. So typically when you're using these drills, you'll drill 1 or 2 holes with them, and rather than putting them back, you just throw them away. Now you can imagine trying to use one of these drills in a machine this large. You'd have no feel for what was going on at all. And a couple of ways of dealing with that problem. One of the ways is with what's called a sensitive chuck. This is a small chuck. Makes it easier to hold small drills, but that's not the key feature. The key to this chuck is it's free to move along this axis. It's keyed in so that when you put this in a regular drill chuck like this and you turn the machine on, the sensitive chuck is coupled into the rotation of the larger chuck, but you're free to grab this ring, which is attached to the chuck through a bearing, and then feed this by hand. So even when you're drilling with a drill that you may find difficult to see, it's possible to get a feel for what that drill is doing when it comes into contact with the part. Another way to deal with this problem of sensing what's going on when you're drilling with a small drill is to use a small drill press. This works a little differently from most bigger drill presses in that the motor, the chuck, are stationary. Hold your parts or clamp your parts to this little bed, and the hand wheel, you bring the part up to the drill. And this is sensitive enough so you can also tell what's going on with a very small drill. In addition, if you look at the plate in the front here, this drill runs at 10,000 RPM. That high drill speed makes it easier to drill and take very light chips and put a light load on the drill. This is a set of standard fractional drills. It goes from 1/16 of an inch up to 1/2 an inch by 64ths of an inch. Now, this helix is also a standard. This helix is here to help draw chips out of the hole that's being drilled. This particular drill is suitable for drilling most materials, aluminum, steel, wood. It's just fine. There are some materials, however, this drill is not suitable. For example, brass and many plastics. The problem with those materials is that this high helix angle tends to work much like a screw and can actually dig down inside the part and then typically pull the part up out of the vise, causing damage to the part, to the vise, the machine, and also possibly to the operator. For those materials, it's a special set of drills like this. I'll compare the two. You can see the angle of the helix is much lower. So this drill tends to scrape rather than cut as it's drilling. It's not quite as efficient at removing chips, but it allows you to safely drill materials that would tend to be lifted up by this type of drill. There are some other materials that aren't drillable by either of these drills, in particular very hard materials, such as hardened steel, and materials that can be actually pretty common around a shop and often aren't looked upon as being particularly hard. Here's a good example. In this shop we do a lot of work on robotics, building up our own circuit boards, and many people want to build custom circuit boards and drill holes in them. This appears to be a relatively soft material and you would think it'd be easy to drill, but in fact it's got fiberglass in it, and the glass is very, very abrasive. So using a regular high-speed steel drill will work for a couple of holes, but after a few holes you start abrading away the leading edge of the drill. So instead of the sides of the drill being straight, they're somewhat tapered like this. So you find as you drill more and more holes, you have to push harder and harder to get it to go through the holes. You notice you're producing more heat, and that's because you've abraded away the part of the drill that does most of the cutting. The right drill to use for these materials is this one. This drill is made from tungsten carbide, and it's much harder than a standard drill. This drill is capable of drilling hundreds or even thousands of holes in abrasive materials like this, or very hard materials such as hardened steel. In fact, this is the type of drill that's used to drill all of these holes in the standard manufacturing process for commercial printed circuit boards. A drill press like this is a fairly robust machine, but even something this massive does have its limitations. This particular machine is limited to drilling holes of about 1.5 to 2 inches in mild steel. In aluminum, that means you can drill something like a 2-inch hole. Going beyond that risks damaging the machine. Some things to watch out for this type of machine: it looks a bit like an arbor press. Got a handle here to pull down. As you pull this down, you drive the quill down, and in fact, functionally it is similar, but this isn't designed to deal with the loads that you generally see in an arbor press. So using it as an arbor press risks damaging the quill feed. The milling machine is very similar in appearance to this machine, particularly because we have this XY table mounted on the drill press. But in fact, this machine is also not particularly useful as a milling machine. The reason for that, I'll demonstrate this, is the size of the quill is nowhere near as large as the quill you typically see in a milling machine. That means that this machine is much more flexible in this direction than a milling machine of a similar size. Also, drill press is typically set up with a drill chuck. And this is a very poor way to hold on to end mills and other milling tools. Everything looks fine so far. It looks very much like what you'd see and hear in a milling machine. And it's sort of working. But you can hear some rumbling, some chatter. We feed this across the part. You can see the surface finish there. There are irregularities in that surface of about 0.010 of an inch. What's happening there, due to the lack of stiffness in this machine, in this direction, the tool was coming down and deflecting considerably each time it was taking a cut. And this is clearly unacceptable if you're trying to produce parts with nice flat surfaces and good surface finishes. This machine is called a bandsaw. It's called a bandsaw because of the shape of the blade. Ordinarily, all you can see of the blade is this little exposed section here that actually does the cutting. This is a blade used in this machine, and you can see that it's one continuous band. If we look inside the machine, by pulling one of these covers off, you can see how the blade is driven. There's an idler wheel up at the top here, and there's a similar wheel down below that's attached to a motor and a transmission that actually drives the blade. A saw like this can be used for many different kinds of cutting operations. One of the common operations will simply be to cut down larger pieces of stock, roughing them out into the near net size for the parts that you want to make. Nothing special about a cut like that, relatively straight. And that's the sort of cut you could make with many other saws. The real key feature to a bandsaw is that due to the narrow blade, it's possible to cut curves. This blade is about 1/2 inch wide. With a blade of this width, it's possible to cut a radius of about 3 inches. These blades come in a variety of widths, thicknesses, and tooth profiles and tooth sizes to accommodate different types of materials and different thicknesses of materials. In particular, if we look closely at this blade has 6 teeth per inch. This is sort of a medium coarse blade for most shop use. This is sort of a general purpose blade in this shop, suitable for cutting most materials with the exception of very thin sheets of stock. The problem there is that with stock that's as thin as this, if you push too fast, it's very easy to get the stock all the way down in between the teeth. You can generate enough force that way to actually break the tooth right off the blade. So it's important to always have enough teeth in contact so that that doesn't happen. Typically the number is 3. If you have 3 of these teeth always in contact with the part, you'll have a good controlled cut. Any less than that and you risk damaging the teeth. With softer materials such as aluminum or plastic, it's very unlikely that you'll damage the blade. There's another problem with cutting thin materials like this with a coarse tooth blade. I'll demonstrate that here. The cut I got was reasonable, and I didn't damage the blade, but the noise associated with cutting these thin materials with a coarse tooth blade is enough to be a danger in the shop. Danger to you and danger to other people working in the shop, because with that much noise around, it's difficult to be aware of what your machine is doing and your machine is telling you about how the operation is going. So it's a good idea with thin materials like this, if possible, to not cut them on a bandsaw at all, but rather use something like a sheet metal shear. This is a general purpose bandsaw. It's set up with a transmission that allows you to set different blade speeds. The machine is now set for about 1,000 feet per minute of the blade across the part. This speed is acceptable for cutting materials like wood, aluminum, different kinds of plastics. This is a piece of nylon, and this is a piece of acrylic. Demonstrate how all these pieces are cut with the blade running at this speed. Wood can effectively be cut at much higher speeds than this, up to and over 5,000 feet per minute. We generally keep the machine set at a slower speed because that just keeps it a little bit safer. Having a blade running at 5,000 feet per minute with teeth this large, very capable of taking off 1 or more fingers with the slightest of slip-ups. With soft materials like this, particular wood and softer plastics, there are times when you want to produce a square cut that can be aided with this guide. You can set the desired angle here, lock it in place, press the part firmly up against the guide, and make the cut. This will only work well with very soft materials. The reason for that is there's a little bit of flexibility in this blade, and the blades are not perfect. The teeth aren't exactly symmetrical. Somebody may have bumped one side of the blade. slightly dulled the teeth on one side. So for any asymmetry in the blade, there's a tendency for the blade to wander a little bit. If you have the part firmly pressed up against the square and are pushing it through the blade and the blade starts to wander, there's nothing you can do to correct for that. So for most materials, I recommend that you simply scribe a line on the part and then move the part around as necessary to keep the blade tracking along the scribed line. Thousand feet per minute is also a very good speed for cutting aluminum. Get a nice clean cut, and the cut proceeds along at a very acceptable rate. What I'll do now is lower the blade speed down to a speed that's more suitable for cutting steel. And that speed is about 100 feet per minute. I'll do that on this machine by going to the back of the machine and here, again, access to the transmission. What I'm doing now is just changing the transmission from high range to low range. There's nothing going wrong here at all. This is just as fast as you can cut steel. This is the reason why many prototypes are built out of aluminum. It's so much easier to work than steel. If you watch this blade, it's moving very slowly. Give you a better idea of how fast it's going. I'll remove the cover. And you can see here that 100 feet per minute is really very slow. But to run the machine any faster than this almost guarantees that you'll damage the blade. You actually heat up the tips of the teeth to the point where they soften and almost melt away. They're abraded away by the steel and the blade will then no longer cut. In comparison to that, I will now set it back up to high range to give you an idea of how different these speeds are. In addition to wood, steel, and aluminum, there are a number of other materials that are commonly used in shops. For example, brass is a common material to use for bushings and other small precision parts. This material should be cut at roughly the same speed that you cut steel, possibly a little higher. Other materials I have here, very common in many shops, are a couple of examples of plastics. This rod is nylon, and this piece of plate is a piece of acrylic. Because of the diversity in the material properties of plastics, you either have to look up in a manufacturer's data sheet to find out proper cutting speeds, or just experiment a little, find out a suitable speed. With nylon, because it's relatively flexible, you can cut this a wide range of speeds and get a very acceptable cut. Material such as this is a piece of acrylic, which is very brittle, can have problems at both extremes. Cutting at low speeds tends to produce some chipping in the cut. So rather than getting a smooth cut down near the bottom of the cut, the teeth in the blade tend to chip out small pieces of material. The cut you see here was done at high speed. And at high speeds, you again have another problem. In this case, you can see the smearing of the material along this edge of the cut. What's happening here is the high speeds are creating enough heat to actually start to melt this material rather than cut it cleanly. So again, with plastics, it's a good idea to experiment in order to come up with the best cutting speed. When set up and used properly, the bandsaw can be one of the safest machines in a machine shop. If the machine is not set up properly or is used incorrectly, it can then become one of the most dangerous machines in the shop. Particular during setup, we have a blade guide and a blade guard. Obviously, the blade guard is set up this high, exposing this much of the blade. You run the risk of not only pushing a part through the blade, but some of yourself as well. You should always make sure that the blade guard is set up just high enough to clear the particular part that you're going to be cutting. Also, your posture is very important. You have to let the machine do the work. So you should stand squarely in front of the machine, balanced on your feet, with your hands firmly on the bed of the machine. Often you'll see people in a shop more like this position, without their hands on the bed of the machine, but rather holding on to the part like this. What can happen here is when you complete the cut, you can fall forward, pushing parts of yourself, parts of your clothing, into the machine. So stand squarely, balanced on your feet, and whenever possible, keep the palms of your hands pressed firmly against the bed of the machine. Much of this is like wearing seat belts, in that you may be perfectly safe if you're minding your own business, cutting a part by holding the part like this without your hands down. But, like not wearing seat belts, you may be behaving yourself, somebody runs a red light, clears you out, you're dead. Here, you may be behaving yourself, somebody else can come through the shop, bump your hand just slightly, pushing your hand through the machine. Through no fault of your own, you're missing some fingers or even a larger part of your hand. So keep your hands down firmly, and this way, any disturbances will not cause your hands to move significantly, and you'll be safe. Something you should also be careful about, there's a real tendency to do this, is to leave one hand here as you're reaching down to turn the machine on. Don't do that. Stay away from the machine, turn the machine on, stand up, get squared up, put your hands down, and then move the part with your fingers. Take a small cut, move your hands ahead, press them down again. Continue with the cut. You could see at the end of that cut, there was no perceptible jump at all in my fingers when the blade finally broke through the part. Round stock such as this can be cut in a bandsaw, but some precautions should be taken. It's very easy, if you don't think about it, to grab the stock at the end and then start the cut. It's possible the blade will catch the stock and spin it. If you're holding on to the end of a sharp piece of stock, you can cut yourself badly. A way to avoid this problem is with a drill press vise. These vices have nice square sides ground on them, and many of them also have the tops ground as well. You can take advantage of this design by turning the vise over, letting it rest on the ground top surface, locking the vise down, and now you have a secure grip on the part, and then you can hold the vise rather than the part and then proceed with the cut.